Hi folks, today I'm going to be talking about Venus and how bright it is currently. Some people have been remarking that it seems brighter than normal, or perhaps it isn't really Venus at all because it seems brighter than they've ever seen it before. So here's a photo of Venus taken on May 18th from Ponza Island off the coast of Italy. You can see Venus on the right, and you can see how incredibly bright it is, not only because it's brighter than everything else in the sky in this image, but also because it's so bright that it's actually producing a visible reflection in the water below. That's pretty significant. You normally don't see something like that in a photo like this with water that isn't perfectly calm unless it's the moon. But Venus is really the next best thing. So, just how bright is it? Well, we can quantify it using AstroImage-J. We can use AstroImage-J to measure the flux of an object, which allows us to calculate its apparent magnitude. The total flux within the circular aperture is recorded in the int_counts function up near the top right. That was the flux for Venus. Here's a flux of a known object, also in the image, Jupiter. At this time, Jupiter had an apparent magnitude of -2. So because we know the flux within the image now, we can calculate the apparent magnitude of Venus. The apparent magnitude of Venus is given by a simple formula of -2.5 times the log of the flux of the unknown, in this case Venus, divided by the flux of the known, in this case Jupiter, plus the magnitude of the known. I've also included a correction factor for the atmosphere, because Jupiter and Venus are at different altitudes over the horizon in the image, so they experience different amounts of atmospheric extinction. But because we know the altitude over the horizon of each object, we can calculate the air mass, and therefore the amount of atmospheric extinction each object experiences and correct for it in the final calculation. Then we need to know how bright Venus was supposed to be. For this, I've applied the old Dan Juan formula, which was created in the early 20th century, and believe it or not, it still works. It matches up with our detected value quite nicely. This means that Venus was exactly as bright as it was supposed to be in the image. It actually reaches its brightest point when it's a crescent phase. That might surprise some people, but as it approaches Earth, it continues to get brighter, even as the phase shrinks. That closing distance causes the apparent size of Venus to increase, and actually increases the apparent magnitude. Now, it's true that at some point, the shrinking phase of Venus will begin to dominate the magnitude and start to dim its brightness as it approaches the sun in the sky. But for a surprisingly long period of time, it continues to get brighter, even as the crescent continues to shrink. But some people have asked, how can we really know that this is Venus? How can we really know where Venus is supposed to be in the sky, and that it really is supposed to be getting closer to Earth right now, and that everything is normal? Well, you can calculate it based on just the orbital elements. I've done this before in a video, and I won't go over it again in exhaustive detail. Here are all the calculations from that previous video and that previous example that I did, but right now we're just going to skip right to the answer for this epoch and this observation, May 18th. So if you do the calculations for May 18th at 1930 Universal Time, here are the coordinates that you get from those calculations. These are geocentric coordinates, so we're not calculating for topocentric parallax, and we're not calculating for planetary perturbations. Nevertheless, despite the approximate nature of these calculations, they're good enough for naked eye observations, and they're also certainly good enough to locate where Venus should be on, say, an old printed star atlas. Now, this star atlas was published 30 years ago, and it was published, fortunately, with Epoch 2000 coordinates, so we don't have to do any more calculations to process our coordinates back to, say, an earlier epoch like 1950. We can simply turn to the page that contains the coordinates that we've calculated and see where it should be on the chart. The x-axis up at the top contains right ascension coordinates. So we locate 6 hours 50 minutes right ascension, which is very nearly 7 hours right ascension, and then we come down to about 25.5 degrees, a little more than 25.5 degrees declination. Right here at this spot, this is where Venus should be on the sky according to the star atlas, and it's located in the constellation Gemini. So we can turn to the page specific for the constellation Gemini to get a closer view of the situation. So here's the chart for the constellation of Gemini. You can see it as a coordinate grid overlaid on top of it. So we come over to 6 hours and 50 minutes right ascension, about 25.5 degrees declination, and right here is where Venus should be according to our calculations, right next to the star Mebsuta. So now we can go back into the original image that we have of Venus, closely crop it on the constellation of Gemini, and see where Venus actually is in the image. When we do that, we see that it is indeed right next to the star Mebsuta, right where the star atlas showed it should be based on our calculations.